Guys, can we start our class at 9 while waiting for your friends? I don't want to repeat the subject. Okay? Is it okay? If your friends come into the class, just inform them we start class at 9.
Okay, miss.
Okay. Go and grab your breakfast first. So good morning, students. So we have been waiting for them for 34 minutes. So I'm not going to wait for them anymore. Only four of you. So I think only four of you interested to continue with today's topics. So far, do you have any question for your assignment or any of your courseworks that I have released last week? So still no response. Okay. So let's continue. Yesterday we stopped until the differences between level 3 half and level 4. So now we are going to see how does your CPU check your results. So subtracting your R1 from R0 is an LU operation. So your LU operation will change the CVNZ status flag inside the PS register. So the status flag can be used to check the results. So status flag checking is the heart of your program control. The status flags are used to determine which of two instruction sequences to be executed and whether or not the body of a loop will be executed. So CDM8 if and fee construct. Okay. So this is how does the if and fee being used in CDM8. So if is structured somehow different from an if statement inside your Python or C++. So if start with the if construct and then you're going to have the instruction to set up your flags. Okay. After that, you're going to put your is condition to check whether your condition is true or not. And it branches to end if it of E when it needs it. Okay. So there will be the instruction sequence. So fee will end the if construct. Okay, and then you execute the rest of your system. So far, do you have any question for this part?
No, miss.
Okay, so next, comparing the subtraction. So this is the example, how does the subtraction was done using if and fee. Okay, so assuming your R0 contains A, R1 contains B. So we will implement the equivalent of Python. So if A is bigger than B, so instruction sequence as follows. If subtract R0 and R1. Okay, first as usual, we need to do the construct. Okay, using if. And then we set our flags. Subtract R0, R1. Okay, is greater. So GT is your conditions, and then you put your instruction sequence and fee. So this one will be work fine, okay, but we just use the sub R0, R1, where we change the content of R1. Okay, so the sub operation, this operation will subtract R1 from R0 and leave the result inside your R1. So the subtraction will modify your flags inside your PS. So the flag can be used to determine whether which of the following relationships of R0 and R1 are true for the subtraction occurs. Okay, so this 1, 2, 3, 4, 5, 6. This 6 condition will be checked. So different patterns of your 0 and 1 in C, B, and Z will indicate different relationship. Okay. So comparing, it is better when you assume R0 contains A, R1 contains B, so that we can implement the equivalent of your Python. So this one we are using comparing. Okay, just now we are doing the subtraction only. Okay, we use the subtraction, but now we are using compare. Okay, so instead of you use your subtraction, we are using compare. Okay. So as usual, just now we have our if, and then just now at the CMP here, we are using sub, right? So we just change the instruction here using compare. CMP is greater. So GT is maintained because you want to test for the greater there, right? And then you put your instruction sequence. Okay. P, it means that you end of your construct. So the CM compare R0 with R1 instructs to subtract R1 from R0 and throw away the results rather than save it inside your R1. But the calculation still will be used to set your flags. Okay, then we proceed. The CMP operations will compare. CMP is comparing R0 with R1. The operation subtract R1 from R0, but without changing either register. Okay, so the subtraction is just to modify your value inside your flags. Okay, so the flag pattern can be used to determine which of the following relationship are true. It's still using the same pattern. It's just that you are not changing the values. Okay, so we can test a different condition assuming R1 content A and R2 content B. So we can implement the equivalent of your pattern if A equal to B. And then you're going to have the instruction sequence. So if CMP R1, R2 is equal, so what will be the instruction will be done and then you end the loop. So here you will compare R1, R2, instruct to subtract your R2 from R1 and throw away your results. Once you throw away your result, we can test to see whether the two registers contain the same bit string or not. Okay? So even if must follow by an is combined with a mnemonic that identifies beyond the condition will be checked, there may be any number of instructions between if and is. All of them will be executed before the condition will be checked. Okay, the if part of an if must appear on a line of its own. It cannot be shared. Okay, so the flag must be set up before the is and must not be changed until after your is statement. So the instruction that set them up for test will be last ALU instruction that is executed before your is, even though we doesn't know how long, but it must be the last one. So every if must end with P. So far, do you have any question for this one? So no. So this is
No.
the if else P construct. So and the CDM may also have an else part. Okay, so you going as we already know just now is a single if. Okay, we add F is a single if. This one is an if else statement. Okay, if instruction to set up your flags, and then you have your conditions, instruction sequence 1, else and instruction sequence 2. And you're going to end your loop. So next, this is an example of how it will be. LT means less than. Okay. So this one is the example of the zero flag. So testing the content of TST. So TST are the mnemonic. So TST R1 means that shorthand to move your R1 into your R1. So this instruction passes the bit string from R1 to ALU and straight back to your R1. So the test operation is used to modify your Z and N flag in your PS register. Both your C and B are set to 0. After execute your TST R1, you can check which of the following is true. Okay, so these 4 things would be checked. Okay, so different pattern of 0 and 1 in Z and indicate different content of your register. So next, the if part of our program in Python, this one will be our usual coding. Okay, but then we have to compare. But in assembler, we need to do some compare. Okay, we cannot directly use this code. Okay, so we need to compare R0 with R1. If R0 contain greater number, we will copy R0 to R2 because that will be where we want the max to be. Else we will copy R1 into R2. Okay, in assembler, to get if R0 is greater than R1, we need to have 2 steps. 1, do the comparison, and second one, we test the results. Okay, so this one. Okay, then if our part, so we will test like this. So if you put this together, we can get a code to find the maximum of your 2 integers in R0 and R1, copy it to R2. So we have our compare, and then check our condition. If it is greater, you will move your value from R0 to R1. Okay, because your R0 is bigger than R1. And then you will move this value into your R2. So this is where your R2 will store your maximum value. So if not, it will use the value in R1 to put in your R2. And then you end your else construct. Okay. So next, after comparing R0 with R1, the machine must be made to copy the content of the write register to your R2. Okay, there are two possibilities whether you want to move from R0 to R2 or you want to move the R1 to your R2. This will be the instruction that appeared in the two arms of your if. So far, do you have any question? No?
No.
So let's proceed. Developing the program back to where we learned about this one. So this would be the previous step, right? Okay, so we will have our open and close. These two things must be done. And then we have our declaration. And then we have to load our value in loop and load again. Okay, and then we have to pause to stop the clock. Okay, so a CDN program where we want to do some the iffy, right? So we will put in the between here. So here is the one that we learned previously. It's 1, 2, 3, right? So these three things we already learned previously. So the one that we learned yesterday and today, we will implement in between of that. So this one is a number 4. Okay, only then we can place the value directly inside your max. Okay, so another example, so find the absolute value of an integer. This is the Python version. Okay, so how do you do it? As usual, we need to create your scaffolding. So these three things must be there. This is the template. Okay, so you have to create your asset where you want to start your address, which part. Okay, and then we will stop our clock and end. Okay, so and then we will do our declaration. Okay, once we do our declaration, we can load our value. Okay, where do we load our value into the things, the variables that we have declared in below. Okay, only then we put our if tree statement. Okay, after that, okay, if you look at here, compare R0 with 0 to determine whether contain negative numbers. Okay, so you will need to find. Okay, so subtraction 0 from R0 is pointless. We just want to know whether your value is or not containing your negative number. Okay, so that will be no use of. So as you can see, this one is mean to find your negative content or not. Okay, and then we add a code to negate your R0. So this would be your condition. Okay, your sequence statement. Okay, only then you add the code to store your result to your ABS. So this ABS is already being declared previously. Okay, so look at the if in this program. So first thing that you have to take note, the absolute value of the number start with R0, it will end up with your R0. So you doesn't need to copy the result to a different register. R0 is either changed or not. You doesn't need an else part to construct your if. Okay, so this would be the sample. If, is, and feed. Okay, so next, using your PS register for control. So PS is your processor status register that contain 4 flags. Okay, that indicate what will happen for the lifetime when your ALU was being used. So each ALU operation will affect some or all of your flags. Okay, so this the pattern of your flag indicative of various conditions. For example, any flag pattern which Z is set to 1 indicate the OLU gave all the zeros result last time was being good. So we can use the current flag pattern to control what of the part of your program can be executed next. So to understand your how was your flags are used, you might look at your flag, the factors that cause them to take the different values and how was they being interpreted. Okay. So next, the PS flag, so CV and execn. So there are four processor status register that you have learned previously, and each of them name for what it signifies. Carry, it means that you contain or carry out from last ALU operation. Overflow, which is your V, will use to indicate whether there will be two complements overflow or not. Z is your zero, set to one when all bits of ALU result was zero. Negative is equal to bit 7, okay, of your ALU results. Okay, so let's have a 10 minutes break before we continue. Okay, so let's proceed. How does this work? Imagine that we just got the ALU to add together two unsigned numbers, and we only have to store the result if it is small enough to represent 8 bits. Because we can ask whether or not to carry out from bit 7 was a 0. So we only care about the C. About the C, so we can ask the CPU to examine your CVZM for the pattern of 0. Fortunately, we do not have to specify the pattern. There is a standard condition of CC carry clear that is true under these circumstances. So this one. Okay, this is how guys the if P will be used. Okay, so if you add R1 and R2, if your return is CC, it is means that carry clear. Okay. So this is another examples. Okay, so we use a Python as all of you already learned about Python. So a CDM8 assembly, we can use an arithmetic shift to the right to divide a number by 2. The quotient is left in your register we shifted, so the remainder is left in the carry flag. Okay, so this, we use the integer division by 2. Suppose we have loaded a number into register R1. So we have SHRA to divide it in by 2. Divide the quotient in R1. So, but how do we assess the remainder? So if SHRA R1 divided by 2, leaving quotient in R1 is CS means that carry will be set if your number was odd. You will load your R2 into your 1. Okay, so we have remainder in your R2, then we will put it as 1. Okay, so else we will load the R2 as your 0 and then P. So by using CS condition, the ifs in the if above, we are asking about is your flex pattern is 1 dash dash dash. Okay, so this will be the sample code for the full assembly language. Okay, so this would be the ALU operation change to your PS flag. Okay, so the operation, okay, and then you have your usage. What will be changed? What will be the operation? Okay, so these two things would be different. Okay, so this one will be the first, this one will be the second, and you can see that the differences between the changes here. Okay, so flag patterns, the flags have been chosen so that they enable us to check the wide range of our different conditions. So each different condition can be detected by looking at a specific pattern of 0 and 1 in your flags. In some situation, we are only interested in one of the flag, in which in which case the flag pattern will be stayed as don't care about the 3 of the 4 flags. In many cases, we are interested in the content of 2 or more flags only. Okay, so this is the examples where your CDF8 can test many different conditions. Okay, and then the horses of the course. So different conditions have been chosen to enable us to check the result of an ALE operation on different types of data. So the platform doesn't know what type of data that we are working with. All it sees are your actually in the bit string. It is your responsibility as a programmer to choose the appropriate data types and to use the correct condition for the data types you have chosen. Whilst the same arithmetic operation may be used on unsigned numbers and two complement numbers, the result need to be interpreted differently. So for example, if you are adding unsigned numbers together, you must examine the C flag to check for overflow. So use CS. If you're adding two complement numbers together, that this will not work. So you must examine the V to check the overflow. So use the VS instead. Okay, different usage will use different type of terms. Okay, so there are two families of comparison condition as well. So first one is comparing your unsigned numbers. Another one is comparing two complement numbers. If you use a condition from the wrong family, you will get the wrong results. For example, GT will be good, will be work correctly when comparing two complement numbers, but won't always give the correct result for unsigned numbers. While for condition high, works correctly when comparing unsigned number, but does not always give the correct result for two complements numbers. So some condition have two names. For example, EQ is the same as ZAC, NAQ, will be the same as your NZ. So this will be a simple reflection of the fact that the same fact pattern may be used in different way. Whilst arithmetic result and numerical comparison are well supported by absolute name condition, there may be situation where you use a condition with name that looks wrong. So what is important is that you know what flag pattern that you want to detect and you choose the right condition to detect it. Okay, so this would be the test that examine just one flag. Okay, you can see the mnemonic, you can see the description. So a dash in your flag means doesn't care whether it is 0 or 1. Next, comparison numbers. Comparison of unsigned numbers work differently from comparing two complements numbers. So the 8-bit unsigned numbers in the range of 0 to 127 are represented by the same bit string as the 8-bit two complement numbers in the range of 0 to positive 128, 127. Comparison of bit strings in the range should give the same result for both representation schemes. But then the 8-bit unsigned numbers in the range of 128 to 255 are represented by bit strings that are used to for your negative numbers range negative 1 to 8 until negative 1. In the two complements representation, your skip. Comparison that involve your bit string in that range may give different result of two representation schemes. So when does the problem will be arise? So when one of your bit string that we compare has the most significant bit set to 0 and the other one has the most significant bit set to 1. When the bit string represent unsigned number, we are comparing a number in the range of 0 to 127 with a number that in the range of 128 to 255. While another one is the bit string represent two complement numbers that we are comparing a number in the range of 0 until positive 1 to 7 with a number in the range of negative 1 to 8 until negative 1. So far, do you have any question for this one? Okay, no response. So next, the example of the problem. So this will be the example of your problem. Okay. You may check you may check the unsigned interpretations. Okay. So A would be bigger than B will be always true. B is bigger than C, false for unsigned number, but true for complements. C is bigger than D, it will be always false. Okay, so D is bigger than E, true for unsigned, but false for your two complement. So you can see that there would be two different interpretation, depends on where you use it. So far, do you have any question for these figures? No? Okay. Next, so what will be the solution? So the result of subtracting one bit string from another is the same, no matter how your two bit strings are interpreted. So for example, your R0 will having 11111 and R1 would be 00000011, where you need to perform the subtraction, where you shall be leaving the value 11111100 in R1 and set your flags into 1001. As an assigned number, that we store the result in R1 is read as 252 and as 2 complement it read as negative 4. Similarly, when we compare the R0 to R1, it will leave your R1 unchanged and it will set your flags into 1001. Therefore, we cannot change how your subtraction works, but we can change how we use the result by employing different condition tests. Okay, so unsigned number test higher than. So if you want to test to see whether one unsigned number is greater than another, we cannot rely on the result of the two complement tests. So we use the GT. Instead, we use the unsigned number test high that tests whether one unsigned number is higher than another one. Okay, so unsigned version is one, two complement version is one. So the difference is in your condition part. One is using high, one is using greater than. Okay. So for example, if your R0 is all 1 for 8 bits, for R1 is 000011, so your R0 will be read as 255 as an unsigned, or it will be read as negative 1 for your two complement, whilst Your R1 values would be read as 3 or positive 3 as 2 complement. So you need to compare. Okay, when you compare, you will set your flags into 100. So as you can see here, the unsigned version and 2 complement version, you going to have very different structure. Okay. For example, as you can see, under your high, you're going to have your sequence instructions here, while inside your 2 complement, you does not have the you does not have to use the high, but you use GT. So the value would be different. It will go into this one. Okay? So the code to find maximum two unsigned numbers, then copy it to your R2. So this would be the example of the code. Okay? So as the first step, you need to put your exec and halt. Okay, this would be the first step. Second step, you will do the declaration. And then you're going to have the third step is this one. Sorry, not the third step. So this one, the comparing is the fourth step. So the third step is the code to load your numbers. So this would be the third step, only then you are doing the comparison. So this would be the fourth step. Okay? So as you can see, exec must have and halt. You must have. So this one will be the first step. The second step is you are declaring, and then you load the values, only then you perform your operation. Okay? So unsigned number test. So this is the mnemonic that you should know, where a dash doesn't mean that it means that it doesn't care whether it is 0 or 1. Okay? So this one is two complement number of tests, GT, LE, and LT. Okay? So that's all for this chapter. So chapter 7 is done. So can we proceed to chapter 8? Okay, so let's proceed with chapter 8 after we can start our chapter 8 on at 10 o'clock. So you can have a break for 15 minutes. Okay, so let's proceed to our chapter 8, Introduction to Subroutines. So, one useful feature is the provision of a stack facilitates the supports of your sub-program. Okay, at level 4, functions of procedure or methods. For level or 3 will be going for your subroutines. Okay, so support for sub-program means that you can write little program that can be used in lots of places within a big program, but without having to have lots of copies. The subroutines actually is a set of instructions that in one chunk of your memory, but used in many places in your program. Okay. So what problem are we addressing? So level 2 set is very limited in the scope. So there are many operations that are not directly available in level as their level 2 instruction. We have to program them. For example, now PDM8 has no multiply operation. So if we want to use the multiply operation, we must write a sequence of instructions that have same effect with your multiply. So every time we want to perform a multiply, we use that sequence of instructions. Okay. So the simplest solution is to insert copy of instruction sequence in each place that we want to use it. However, code copies take up your memory, which is critical resources for a small system. So copies are identical only initially when the program is first written. So whenever an engineer needs to modify the code, they have to remember to modify all the copies consistently. So this is a potential source of errors that are difficult to detect and fix. So what we really need is a way of using the code sequence without having lots of copy of it. Okay, so most of the platform provide a means to refer a common code rather than replicating it, but specifically there is an instruction that is used for these purposes. So JSR address. So where the address is start address of a common segment of code, such segments are known as your subroutine. So this is most commonly seen in the form of JSR name, where the name is the label associated with the start of your address of the common segment of your code. So let's jump into your subroutine. So GSR instruction perform the jump to your subroutine. Caller, it means that the program that jumps to your subroutine. So the jump itself is often termed as a subroutine call. So consequently, the subroutine may be referred as the calling. Okay, so how it works? Instructions are placed in the memory with certain addresses, then these can be labeled in the assembler. So we can label your memory location of any kind of data based for data and instructions. The name in GSR instruction is the label placed at the beginning of your subroutine. So the function of GSR change the control flow of your program instead of passing the control to the next instruction. Okay, for example, it occupying the next memory cell, so it pass it to the point labeled as name. Okay, so example of your program. So the program on the next slide performs a straightforward calculation like this. So memory E equal to memory A times memory B plus memory C times memory D. So this is not complicated, but your CDM machine does not support multiplication directly. Therefore, we need to have a sequence of instruction each time when we want to multiply of two numbers. So if pairs of numbers we want to multiply are put in the same register each time, we can use the same sequence. Therefore, we are going to use a name subroutine to perform your multiplication. So this is the sample of the code. Okay, as usual, we have our exec, halt, and end. And then we will have our data area, which is your declaration. We have your load. And then we're going to have your, what we see, the operations. Okay. And then we're going to add on your subroutine. Okay. JSR multiply. Okay. So and then next, return from subroutine. So the subroutine will be executed, the instruction after instruction until platform encounters the instruction RTS. So RTS restore control back to where it was. It passes the control to instruction that immediately follows the JSR that caused the jump to the subroutine. Okay, so JSR means for jump to subroutine in the first place. Okay, RTS is known as return from subroutine. So it will be the pair lah. Okay, so this will be the example of your code. We will have our exec. We will have our exec, and then you have our program, and then we will put our halt. And then we have our subroutine values, and this is our declaration and our end. So the role of the stack, one of the register that can be pushed onto and pop off. The newest one, the stack is known as PC. Okay, so this is how your subroutine are managed. So JSR jump to subroutine, special kind of push. RTS is written from the subroutine, especially for the kind of pop. So far, do you have any question for this one?
No.
Okay, next, subroutine and the stack. So the stack is used to call for your subroutine. So operation JSR push the current contents of your PC onto your stack and then copy a new address into your PC. So JSR 0x0 push the current content of your PC onto the stack and copy the address of 0x50 into your PC in its first place. So JSR multiply push the current content of the PC onto your stack and copies the address multiplied into the PC in its place. So the effect of this is the same as you perform the branching to the instruction labeled as multiply. Okay, except we have to keep a record where we were before the branch was taken. Okay, so next JSR 050 is meaning. So this 0x50 is the start of your address for your subroutine. So 0x50 is copied from into your PC. So the next instruction will be executed. Okay, to be executed will be the one who finds in the memory of the 0x50 GSR. Multiply is so MLT is the start address of your subroutine. So MLT is copied to your PC so that the next instruction to be executed will be the one found in your memory MLT or memory multiply. So the machine will continue executing the instruction in strict sequence from the start of your subroutine until told to do otherwise. Okay. Then let's proceed to the second step. Okay, the stack is used to returning from your subroutine. So you're going to have your operation of RTS. So usually RTS will pop your top item off the stack and put it into the PC. So the effect of this to return executing program from instruction after GSR that is known as your subroutine. But this one only works if the top item on the stack is the address that was pushed onto it by your GSR that transfer control to the subroutine. Therefore, you must be very, very careful about what you want to use. Okay, the stack inside the body of any subroutine. Okay, so this is the example when you use the multiply of subroutine call. So if we have a level 2 multiply instruction, we should expect only R1 to be changed. Okay, so this is the example of subroutine algorithm. Okay, so this is the code. So multiply is the dirty subroutine. So subroutine we are supposed to writing is for it to perform operation R1 is equivalent to R0 times R1 and nothing else. But you have to understand that algorithm that we have chosen, it cannot do its job without using and changing at least one of the other register. Okay? So our multiply subroutine modifies a register that it should leave unchanged. It is a dirty subroutine. So this is a problem for calling your program because the register may contain important data. So this is the example of your code. Okay. So the stack may be also saving the state of the CPU before they call for your subroutine. So this allows us to protect the main program from the subroutine. Therefore, we assume that a subroutine, especially one that was written by another program, can or will make the use of any or all register without the consent of for you to call the program. So we push all register containing essential data onto the stack before issuing the JSR instruction. After that, we pop them off the stack after the subroutine with it. And the essential data has been restored. Okay. So this is the example of multiply subroutine call. Okay. This is the procedure. This is the sample code. Okay. Alternatively, a clean subroutine may be used to stack upon entry to save the state of register that it should not change. The content of this register may be restored immediately after returning to the main program. So we will start by writing the subroutine so that it only affect those registers that are used to return the results. We push all the register we should leave unchanged upon return onto the stack before we process the data. Then we pop them off the stack before subroutine return and the extension data has been restored. So this one would be the algorithm, and this would be the codes. So passing the data in our example, we use register, right, to transfer your data between calling the program and subroutine. So your data was transferred in via register 0 and register 1. And your result would be transferred out via register 1. So this work okay, but for only small subroutine that require very little data. But what if we have 4 registers? So it is impossible to work this way if your subroutine needs more than 4 bytes of data to perform the job. Passing parameters in your register make the implementation of recursion is difficult. So if you found that recursion is a new word for you, so I hope you can perform some class activity to find out what is it about recursion, because later on you will use the recursion statement in your assessment. Okay, so using your shared memory, it means that a subroutine needs several bytes of your data to do its job. It may be convenient to set up a label, which is your shared temporary memory area. Okay, so the calling program will store your data to a shared area. So your subroutine will load your data from the shared area, and then they will store the result to the shared area. So your calling program will load your result from the shared area. So far, do you have any question for this one? Okay, no. So let's proceed. So this is the example of your algorithm using multiply version 2. This will be the code, continuation of your code. Okay, so this one will be the algorithm. Okay, so this one would be your codes. So the problem using a shared memory. So shared is a static memory can works, but it requires additional register to do the storing and loading. It requires us to reserve memory space that persists of the lifetime of the program. So static allocation of the memory. Each subroutine needs its own shared memory area. Therefore, the program must has a larger memory footprint. So it will be potentially slow because it does not support recursive call for your subroutine. Okay, so therefore we want to use the stack to pass your data. We know that your register content can be pushed to the stack and pop up again in reverse order. Well, this one will help us when we running out of our GP register. So what is GP register? So I hope you already know what is this. I don't ask me this kind of question again. It is also used to implement your GSR and RTS. If you forget what is GSR and RTS, just flip back your slides. Okay, it will be indefined. So in fact, the stack is just another section of your memory. So we can use it to transfer your data in or out of your subroutine and to hold your temporary data using your subroutine execution. This is common in your level 4 platform that offers your procedure, function, and methods. So the amount of your data that we can put on the stack limited only by how large it is. However, passing large amounts of data to and from your subroutine via the stack cannot be done using a simple set of push and pop operation. Okay, we put a temporary stack data area on the stack just before your JSR. So by calling the program, makes room for the shared data on the stack and store your data or to the shared area of your stack. Okay, subroutine call where your subroutine will use the data from the shared area. Immediately after your RTS has been executed, the calling program loads the stack pointer again and will read as the start address of the shared data area where your result may have been left by your subroutine. So this can be copied or saved as appropriate. And then your calling program publishes up the stack by changing the stack pointer back to what it was before the room was made for the shared data schedule. So this one would be the algorithm. Okay. This one would be your the full code. Okay. Let's continue with how was the stack being used to pass the data. So the TDI we will provide a special stack operation. Okay, so LDSA, RM, N, so where you will copy your SP plus N into your RM, so where your N can be negative values. Add your SP N, so add your N into your SP, where your N still can be a negative numbers. So this will allow us to copy and change the stack pointer. We use the add as p to add your negative n to the stack pointer to make it look like n byte of data has been pushed onto the stack. So we now have an n byte address in S2. We get the addresses of the item in this as our data area using obviously and use your LP and FP to store to copy the data to and from your data. Once finished using the data area, we must take the stack center back to where it was by adding negative n to the stack of S3. Okay, so this would be the sample of the code. Okay, so the subroutine uses the shared data area on the stack. Using JSR to call subroutine decrements the stack pointer by 1 automatically, so the start address of the shared data area is #e plus 1. So the subroutine loads your S3 plus 1 into the register to see the start address of the shared data area. It can then access but not pop the data from your shared data area. It also transfers the result to the shared data area. Push and pop can be used to sync and restore your register within the subroutine. Okay, so let's have a 15-minute rest before we proceed to the next one. Okay, let's finish our slides. So using the stack to pass your data, so your subroutine uses the shared data on your stack. So they will use a JSR to call your subroutines decrements by the stack pointer by 1 automatically. So the start address of the shared area would be SP plus 1. So the subroutine will load your SP plus 1 into your register to give the start address of your shared data area. Then it access the data from the shared data area. It can also restore your results to this shared data area. Push and pop can be used to save and restore your register within your subroutines. Okay, so this would be the example of the algorithms. So this would be your codes. And then we can clean up our subroutine by saving all the register to the stack on entry and restoring them just before exit. Using GSR to cause within increments the stack pointer by 1. So start the address of your shared data area is SP plus 1, pushing all the register to the stack decrement to the stack pointer by further 4. So the address of the shared data area now will become SP plus. So your subroutine will load your SP plus file into your register to give the start of address of your shared data area. Only then it can access but not to pop your data from the shared data area and can be used to store your results the shared data area. Okay, so this is the clean subroutine algorithm. So this will be the code. So passing addresses as a parameter, so all three of these techniques can be used to pass copies of data items into and out of your subroutine. So what if the data item is very large and what if you want to give subroutine access to the original data item in your memory? So in these cases, we may arrange for the address where the data item can be found to be passed as your parameter rather than you copy your data item. So this usually the address of your original, but it can be the address of a copy. Okay, so the value and addresser would be different. So when a copy of your data item is passed to a subroutine, we say that item would be being passed by value. So changes made by the copy inside your subroutine, okay, inside your subroutine does not affect the original. So therefore, this is a good discipline because because the calling program that is owner of the data item, not the subroutine. And it is responsibility of the owner itself to determine how and when a value should be changed. However, making copies take time and uses resources. Okay, usually your memory lah. And if the data item is very large, okay, for example, you use an array, the creation of copy can be prohibitively expensive. But the difference when we use the address of the data item is passed to a subroutine, we can say the data item is passed by reference. Okay, if we copy pass by value, if address of your data item, we pass by reference. So your subroutine have the access to the original item. Okay, any changes on your data item can be made by the subroutine are changes to the original. So this include the changes made in the course by calculating a result which we may not wish to see the propagated to the original data item. So this can have serious consequences if the calling program is relying on the original data item remaining unchanged as a result of your subroutine. So usually passing parameters by value is safer than passing them by references. So these two things, I hope you can understand the differences. Okay, so next example of bubble sort. So we have two types, version 1 and version 2. So version 1, we only use the register, while version 2, we are using stacking. So I heard bubble sort you already learned in your subject. Bubble sort. Dalam subjek mana macam? In your CPS, you already learned about bubble sort. So I don't think this is an issue for you to understand this. Okay? So take note for version 1 when you are using register. Okay, so an n element array is stored in your n plus 1 byte of your memory. So 1 byte containing the length of array, followed by n byte, which is your array elements. So the start address of your array is the address of the cell where the array length is stored. So first load the address of your array into your R0, then call the bubble sort 1 using JSR. Sort the array into ascending order and return to calling program using RTS. But if we are using stack, first we set up the stack frame for the parameter where we use the SP equal to SP minus 1. Make room to the stack, okay? Store the start address of the array to your memory SP, and then you call your bubble sort 2 using JSR, sort the array, and then return to calling your program. So the things is same like this. It's just that the way you use it differently. One is using the register, another one is using stack. When we talk about stack, you will put in a like this. Okay, and then you will destroy the stack frame. Okay, and then you restore back the stack pointer like this. Okay. So next, local variables. We can give a subroutine a section of memory to use as its own private data area. This can be used to accommodate variables and used by your subroutines. As long as the content of this data area are not shared with the main program or other subroutine, it is local to the subroutine, therefore it is known as your local variables. So this data area may be provided dynamically via the stack. Additional bytes are added to the stack frame, will not be used either to pass your data in or to pass the result out. So this space is allocated to the subroutine when it is called and surrender when the control returns to the calling point. So local variable therefore have a limited lifetime. Okay. So next, why we need to go all of these troubles by looking at this from the perspective of a simple multiplication subroutine, it looks a little bit much. Okay. By setting up a set memory areas required a lots of instruction, may we use several registers. Therefore, we calling the subroutine and collecting the result is much more complicated. So the program will be much more longer. But still, they have their own advantages where by using the shared memory means subroutine can be sent as many parameters as we like without running out of register. Okay, using the stack dynamically means your subroutine does not need their own static data areas and can be provided with space to accommodate local variables. Passing addresses really comes into its own when dealing with arrays and string and other data structures. Includes parameter passing and the mechanism that we have looked at to support it, especially using the stack. It is most useful to working with the level 4 platform. Okay, for example, your Python and C++ and C lah. So passing parameter by address mean that function can deal with the large data structures without having to do a lot of copying. Using the stack to pass your parameter and to return your result means that we can implement your recursion. So individual parameters do not have to deal with your complexity of setting up shared memory areas, as it can all be handled by the software that translate your program from level 4 to a set of level 2 instructions. Okay, I think that's all for today. So tomorrow we don't have class and tomorrow is your public holiday. So please be prepared for your test next week. And please be punctual. I doesn't like the way you act now. Thank you. So see you when I see you. Bye bye.
Thanks, Grace. Bye, Miss.
Thanks,
Bye,
Miss.
miss.